Hello, IBSL2. Tonight's topic is normal distribution. And what we've been doing before now has been discrete random variables. Now we're going to be looking at continuous random variable x when they're, so continuous would have measurable data. And most of this, what's going to be shown in the slides today, you should have on your paper. Hopefully you took that home from last class. And if you lost the paper or were absent, you can also get it from the website. And it'll help you with some of these graphics, less to write down. So first of all, realize that the probability density function of a random variable x is just showing you that the probability of that x occurs is between a and b is the area under the curve of your function. So our variable of a and b, what you're finding is this area under the curve. So the probability of x being between a and b will be this area here under the curve, this section from a to b. And the really interesting thing about the normal distribution is that you've seen that in the following natural cases. So one example we're going to be talking about tonight is like the chest size of English males. They also, I've seen it talked about with birth. Babies are born and the average, they're distributed normally. Also like errors in a manufacturing process. The lengths of adult female tiger sharks. And then the one you've heard the most probably in your school lifetime are scores on tests taken by a large population. And x is normally distributed, the probability density function actually looks like this. In Algebra 2, when you learned about the normal distribution, you probably were not shown what the function equation was. We are going to be talking about it in class more than I am in the notes about how it is derived and how you get certain parts of it. But tonight I'm just going to be touching on it, and then in class we'll talk about it more. But this function, though, is for all x values from negative infinity to positive infinity. And it's going to be symmetrical about our mean here. X is mean. So if you think about remembering from Algebra 2, our mean always went to the right here in the center, and all the data is symmetrical around your mean when it is distributed normally. If you think about any function that we have, and we've been doing in IBSL2, when we have the function and we take the first derivative, remember we would find the maximum if we set it equal to 0. So we can take the first derivative of this function, then set it equal to 0, and you'll find when we do the math that it is equal to the mean. Other things to realize is that the function, the area under the curve from negative infinity to positive infinity, is equal to 1. So the entire area under this curve, remember the area under this curve would be 1. So the antiderivative of the function would be equal to 1. As well, if you think about the second derivative, when you set that equal to 0, that is talking about the inflection points. Anytime we set our second derivative equal to 0, we're finding the inflection points. And if you look at our curve here, you can see the inflection point where the concavity is changing is right about here in this section, and then in here on this section. And if we look at our normal chart here, we can see that's where the standard deviation is. So when we set our second derivative to 0, you're going to have 1 standard deviation. Okay, so and we're going to be talking more about the math and finding the first and second derivative in class. The part I want to review tonight to bring back before we do that is the Algebra 2 part that you learned a couple years ago, and that was the empirical rule, where within one standard deviation you have 68.26% of the data. So remember, our mean is written in the right here in the center, and then going from here to the positive we would be adding standard deviation. So from our mean to our first section, you'd have the mean plus the standard deviation, and then this would be our mean plus 2 standard deviation, and then one more would be our mean plus 3 standard deviation. When we go in the negative direction, we'll be subtracting the standard deviation. So and here would be our mean minus our standard deviation, and then you mean minus 2 standard deviations, and then mean minus 3 standard deviation. So within one standard deviation of the data, if the data is normally distributed, you'll have 68% of the values. So this is our within one standard deviation, would be 68.26%. Within 2 standard deviation, if it falls normally, then it's 95.44%. So pretty amazing. Within 2 standard deviation here, that would be 95.44%. Okay, within 3 standard deviation, you have almost all of the population would fall from, and that is 99.74% of the data falls within standard deviation, within 3 standard deviations. So the only part that doesn't fall within 3 standard deviations is this small part here, which is 0.26%. So on below 3 standard deviation, mean minus 3 standard deviation would be 0.13, and then above would be 0.13. Okay, so pause the video, make sure you have all this written down. We're going to be using this with the next problem. All right, so whenever you see a question with normal, this is one of the first things you'll be thinking about. And I'm just going to read our question and talk through how to do this problem. The chest measurements of 18-year-old male footballers is normally distributed with a mean of 95 centimeters and a standard deviation of 8. So the first thing you're realizing, okay, it's normal distributed data, and the mean is 95, and our standard deviation is 8. And whenever I see normal, I'm going to be thinking about this curve. And my first step is to start at the mean here, and then add my standard deviation in the positive direction and subtract in the negative. So this point here would be the mean plus our standard deviation. So in this case, 95 plus 8, so that'd be 103. And then we would add 8 more, so it'd be within 2 standard deviation. That would be 111. And then adding 8 more would be 119. In this direction, we're going to subtract 8. So we have 87. And we would keep subtracting. So subtract 8 would be 79. And then 71. So if you look at this problem, number AI here, they wanted to find the percentage of the footballers with chest measurements between 87 centimeters and 103. So, and you can see that 87 falls on this exact value here, so we can use our empirical rule and then 103 as well. We can use our empirical rule where we know that this is 68.26%. So our answer for this first one is 68.26%. Then if it falls between 103 and 111, they're talking about this section here. Okay, and remember from our graph there that that percentage is 13.59%. So go ahead and pause the video and try part B. So for part B, you should realize it's from 87 all the way to 111, which is the two sections we just talked about. So you can add your two percentages and get 81.85%. All right, so there's some ways to do this also in the calculator, and because sometimes it does not fall exactly at a standard deviation. So I want you to go ahead and read this in your notes, this section about how to use the calculator, and pull out your calculator and have that ready. Okay, so the shade normal is pretty neat to see how the graph looks like, and you have to set it up using these parts in our window here. For the x minimum, you have the mean minus 3 standard deviation. So in this case, in our example here, we would have the minimum before for x, and then the maximum would be the mean plus 3 standard deviation. So that would be, in this example, 16. And then our y minimum is always 0, and our y max is 0.2. And we're going to be using these instructions now once we have our window set up, and it wants us to find the probability of x between 8 and 11. And we're going to be using these distribution and select draw, and then we're going to be putting shade norm in, and you want to put the least, so L, the greatest, so upper, and then mean, we have a M here, and then standard deviation is our sigma. So we can, easy way to remember that is LUMO, and we're going to be putting that in and checking out what it looks like. Make sure you clear your draw after each question. So we're going to go to distribution. So second vars will be distribution, and then go over to draw. Now we're going to hit on shade normal, and we're going to input our data of 8 for the lower limit, 11 for the upper limit, and then 10 for the mean, and then 2 for the standard deviation. And then this is pretty neat. So that is showing you the area under the curve, and it actually finds the value for you as well, 0.533. Between each one, you want to clear your data, so you do that by going to second program for draw, and then hit enter to clear it out for each time you want to try. So this one found our area under the curve, remember, is our probability to be 0.533. I want you to go ahead and try using the calculators, try to set up your lower, upper, mean, and standard deviation, and you can use the shade norm or the normal CDF to find the same answers. So go ahead and try that and then bring it back. So you should have found your probabilities to be 0.309 in this case for all. And here, when you're representing greater than or equal to 11, you're going to be using infinity as your upper limit, and then less than or equal to 9, you're going to use negative infinity to represent your lower limit. All right, last topic is talking about z-distribution or standard normal. And for a random variable x that is normally distributed, we can transform any x value to a z value by using this formula. Please pause the video and write this formula in, and then the function. So this is found by replacing x with z, and mu with 0, and standard deviation with 1. The reason you use distribution, z-distribution, is that it allows to standardize the data and compare different data sets, and if you don't have to know the mean and the standard deviation. So I want you to go ahead and try problem A using the x value and the z-score with the calculator. bring it back. So your z-score is 1 and both probabilities